So to begin this chapter, I would normally start the class off with a demo. Work is very strongly discouraging anyone from going on campus unless they absolutely have to, so that includes me. It means I can't go grab equipment and bring it home to set up my own video to do the demo. So what I'll suggest is you have a read through page 837 that introduces the topic, and then watch at least the first minute of, you don't have to watch the whole thing, but at least the first minute of a video on YouTube called Electromagnetic Induction and Faraday's Law by Michael, probably Mellick, I'm not quite sure. Anyway, that's pretty cool, and that introduces the whole idea of what we're going to get talking about next. So where we're going to go with this is, let's go back to the beginning of the chapter, and we said that Ørsted discovered, quite by accident in a classroom demonstration, that if you have a current carrying wire, it's going to produce a magnetic field. And he did this by mistake. He had lots of equipment on his desk, he hooked up a circuit, and as soon as the current flowed, he saw a magnetic field. So that happened with Ørsted, and it kind of begs the question, does it work in reverse? So we know that if we had a current, we get a magnetic field. Is the opposite true? And that's what Faraday studied. His studies were also prompted by accident. Faraday was working with circuits. He had a few on his desk. He opened and closed a switch in one circuit, and what he saw was he had an ammeter connected to a totally different circuit, and when he opened and closed the switch in one circuit, the ammeter on the other circuit jumped. He did see current. So he kind of made a transformer by mistake right in the middle of his experiments. So what Faraday asked and what Faraday studied was, if we change a magnetic field, can we get a current? Of course, one super important application of this is power generation. So let's start to look at this a little bit. But first, we'll have one more application before we get into the math and all that stuff. And that application is magnetic braking. That incorporates the idea of magnetic force along with induced current. So again, I would normally do a demo of magnetic braking in class. Here's another video by the same guy as the last video. It's called Eddy Currents and Magnetic Braking of a Pendulum by Michael Mellick. Watch about at least the first minute and a half of this one, and it shows that when we move a conductor in a magnetic field, we get forces on them, and that force will oppose the motion and start to slow it down. And we're going to do all the math associated with this. We're going to see where it comes from. But this in particular is a really great technology because it reduces the wear and tear of what you're trying to slow down. So brakes in most cars, when you go to slow down, when you hit your brakes, a caliper actually squeezes on your brake pads. It's why you have to change your brake pads so often. So it squeezes on it over time. The rubbing between the two surfaces just wears down and you have to replace them. Magnetic braking, nothing rubs. So there is no wear and tear. So it's a more efficient way to brake things. And magnetic braking is used in lots and lots of things like superconducting trains and stuff. So anyway, that's kind of interesting. The next thing we'll get into is the math that's associated with these ideas and where it all comes from.